Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like memory hierarchies, multi-core processors, multi-threaded processors, vector processors. Let's get started. Slide 1. Memory hierarchies definition and importance. In modern computing, the memory hierarchy plays a crucial role in balancing speed, size, and cost to optimize performance. Since faster memory is more expensive and limited in size, systems use a tiered approach to ensure efficient data access. The memory hierarchy consists of multiple levels. 1. Registers. These are inside the CPU, the fastest and smallest memory, storing temporary values for immediate processing. 2. L1 cache. Located next to the CPU core, it is faster than RAM and holds frequently used instructions. 3. L2 and L3 cache act as intermediate storage, balancing speed and size. 4. RAM, main memory, the primary working memory of a computer, storing actively used data. 5. Solid-state drives, SSD, non-volatile storage that is faster than traditional HDDs. 6. Hard disk drives, HDD, slower but cheaper and larger in capacity. 7. Cloud, external storage, stores data remotely, often used for backups and extended storage. Example. Modern processors use a multi-level cache system, L1, L2, L3, to minimize data access delays and improve overall processing speed. Significance. Understanding memory hierarchies helps in designing efficient computing architectures. It reduces bottlenecks, improves CPU efficiency, and ensures that the system runs at optimal speed without unnecessary delays. Slide 2. Memory hierarchy characteristics. Each level of the memory hierarchy has unique characteristics that affect computing performance. Let's explore some of the key features. 1. Speed versus capacity trade-off. Faster memory, like cache, has lower capacity, while slower memory, like HDD, offers higher storage. 2. Latency differences. Registers and cache have the lowest latency, whereas HDDs are slower due to mechanical parts. 3. Cost factors. Cache memory is expensive, making it limited in size compared to RAM or storage. 4. Data access strategy. Modern CPUs use caching and prefetching techniques to access frequently used data faster. 5. Persistence. RAM is volatile, loses data when power is off, while SSD and HDD store data permanently. 6. Bandwidth optimization. High-speed memory improves data transfer rates, ensuring smooth execution. 7. Energy efficiency. Faster memory components consume more power but reduce computational delays. Example. A gaming PC uses an SSD instead of an HDD for faster game load times and L3 cache to improve processing speed. Significance. An optimized memory hierarchy allows for efficient computation, faster application execution, and better overall system performance. It plays a key role in high-performance computing, HPC, AI workloads, and cloud-based applications. Slide 3. Multi-core processors definition and working. With increasing computing demands, traditional single-core processors became a bottleneck. Multi-core processors were introduced to divide processing tasks across multiple cores, improving performance and efficiency. Each core in a multi-core processor can independently execute instructions, allowing for parallel task execution. How multi-core processors work. 1. Parallel execution. Each core processes different tasks simultaneously, leading to better utilization. 2. Shared cache memory. Cores share access to a larger cache to reduce memory fetch delays. 3. Thread-level parallelism, TLP. Each core can handle multiple threads, improving efficiency in multi-threaded applications. 4. Power optimization. Multi-core processors consume less power per task by distributing workloads. Example. A 16-core AMD Ryzen 9 processor can handle multiple applications simultaneously, making it ideal for gaming, video editing, and AI training. Significance. Multi-core processors are essential in high-performance computing, cloud computing, and scientific simulations. They allow for efficient multitasking, enhanced performance, and reduced processing time. Slide 4. Multi-core versus single-core processors. With increasing demands for high-speed computing, single-core processors became inefficient in handling modern applications. This led to the development of multi-core processors, which integrate multiple processing units, cores, on a single chip to enable parallel processing and improve overall system efficiency. Let's compare multi-core processors and single-core processors based on key performance factors. 1. Execution speed. Multi-core processors execute multiple instructions at the same time, significantly reducing processing delays. Single-core processors execute one instruction at a time, leading to slower task completion. 2. Power efficiency. Multi-core processors distribute workload across multiple cores, reducing power consumption per core. Single-core processors require higher clock speeds to match multi-core performance, leading to more heat generation and higher power usage. 3. Task handling. Multi-core processors can execute multiple applications simultaneously, making them ideal for gaming, AI, and cloud computing. Single-core processors struggle with multitasking and are mainly used in simple, low-power devices like IoT gadgets and embedded systems. 4. Cache utilization. Multi-core processors share L3 cache memory, allowing efficient data access across cores. Single-core processors depend entirely on their own cache, which may lead to performance bottlenecks. 5. Use cases. Multi-core processors are widely used in AI, gaming, cloud computing, and scientific simulations. Single-core processors are more suited for low-power applications like smart sensors, microcontrollers, and embedded systems. Example: a quad-core Intel Core i7 processor can run multiple applications simultaneously, such as video editing, web browsing, and gaming, without slowdowns. In contrast, a single-core microcontroller in an IoT device can only perform basic tasks like reading sensor data. Key takeaway: multi-core processors are the foundation of modern high-performance computing, enabling faster execution, efficient multitasking, and power optimization. They outperform single-core processors in almost all modern computing environments. Slide 5. Multi-threaded processors definition and functioning. In modern computing, applications require efficient multitasking to handle multiple tasks simultaneously. Multi-threaded processors allow a single core to execute multiple threads, tasks, at the same time, improving performance, resource utilization, and responsiveness. Multi-threading is particularly useful in high-performance computing, where tasks like AI computations, database management, and cloud services require simultaneous execution of multiple operations. How multi-threading works. 1. Simultaneous multithreading (SMT). A single processor core can execute multiple threads simultaneously, reducing idle time. Enhances the parallel execution capability of CPUs. 2. Parallel processing. Instead of executing one task at a time, multithreading breaks tasks into smaller threads that run concurrently. Improves efficiency in multitasking applications like cloud computing and gaming. 3. Hyper-threading (HT). A proprietary multi-threading technology by Intel that allows a single core to act as two logical cores, increasing processing power. Example: a 4-core Intel processor with hyper-threading (HT) can execute 8 threads simultaneously, improving multitasking efficiency. 4. Improved resource utilization. Multi-threading ensures that CPU resources like ALUs, registers, and cache are used efficiently. Reduces CPU idle time, maximizing hardware performance. 5. Thread synchronization. Ensures that multiple threads running on the same core don't interfere with each other. Uses techniques like locks, mutexes, and semaphores to manage thread execution. Example: imagine an online game server that needs to process multiple players' actions at the same time. A multi-threaded processor allows different threads to handle game physics, graphics rendering, and network communication simultaneously, improving performance and responsiveness. Significance: multi-threaded processes are widely used in databases. Query execution is parallelized for faster results. Cloud computing enhances virtual machine performance in cloud environments. Real-time applications improves responsiveness in gaming and financial trading systems. AI and machine learning parallel processing speeds up training models and data analysis. Key takeaway: multi-threading maximizes CPU efficiency by enabling parallel execution of tasks, making it essential for modern high-performance computing. Slide 6. Multi-core versus multi-threaded processors. Modern processors use two main approaches to improve performance: multi-core processing and multi-threading. While they may seem similar, they serve different purposes. Multi-core processors use multiple physical cores to execute tasks in parallel. Multi-threaded processors use a single core to efficiently switch between multiple threads, improving task execution without adding extra physical cores. Explanation of key differences. 1. Processing units. A multi-core processor has two or more independent cores that process instructions in parallel. A multi-threaded processor has a single core that executes multiple threads by rapidly switching between them. 2. Execution speed. Multi-core processors increase speed by running multiple tasks simultaneously. Multi-threading improves speed by optimizing task switching within a single core, reducing idle time. 3. Task handling. Multi-core CPUs are better for heavy parallel workloads like AI, video editing, and scientific computing. Multi-threading improves efficiency for tasks that require frequent context switching, like real-time applications, e.g., game physics calculations. 4. Best use cases. Multi-core processing is best for data-intensive tasks that require massive parallelization, such as cloud computing and deep learning. Multi-threading is ideal for real-time applications that demand fast, responsive performance, such as financial trading systems and interactive web applications. Example: a multi-core processor in a gaming PC allows simultaneous execution of game physics, AI, and rendering. A multi-threaded processor in a database server helps manage thousands of user queries efficiently. Key takeaway: multi-core processors excel in raw performance and parallel execution. Multi-threaded processors maximize single-core efficiency for real-time applications. Slide 7. Vector processors definition and advantages. In high-performance computing, vector processors play a crucial role in speeding up numerical computations. Unlike traditional processors that execute one instruction per data point, vector processors use single instruction, multiple data, SIMD, which allows one instruction to process multiple data points simultaneously. This is particularly useful in scientific computing, artificial intelligence, AI, and financial modeling, where large amounts of numerical data need to be processed quickly. Breaking down the advantages. 1. High-speed parallel execution. Vector processors execute a single instruction across multiple data elements at the same time. This reduces the time required for repetitive calculations. Example: instead of multiplying numbers one by one, a vector processor can multiply an entire array in one go. 2. Efficient for large datasets. Works well with big data, simulations, and deep learning applications. Used in weather forecasting models that process thousands of data points simultaneously. 3. Reduced memory bottleneck. Traditional CPUs fetch data from memory multiple times, slowing performance. Vector processors fetch data once, apply operations to multiple elements, and store the results efficiently. 4. Optimized for floating point operations. Many real-world applications rely on floating point calculations, e.g., AI, physics simulations, and image processing. Vector processors optimize these operations, making them faster and more power efficient. 5. Improved power efficiency. By reducing instruction overhead, repetitive fetching and decoding, vector processors consume less power per operation. Useful in low-power, high-performance computing like mobile GPUs and AI accelerators. Example: NVIDIA Tensor Cores leverage vector processing to enhance real-time AI-based image processing. Intel AVX advanced vector extensions improve scientific simulations and cryptographic computations. Significance: vector processors accelerate computation-heavy applications by executing instructions in parallel. They are widely used in AI, machine learning, scientific research, and real-time simulations. Key takeaway: vector processing is a key technology behind modern high-performance computing, allowing faster execution of large-scale numerical operations. Slide 8. Multi-core versus vector processors. As computing demands increase, different processor architectures are used to handle various types of workloads efficiently. Two important architectures in high-performance computing (HPC) are multi-core processors and vector processors. While both improve processing power, they do so in different ways. Multi-core processors focus on handling multiple tasks simultaneously, while vector processors specialize in parallel data processing for numerical and scientific computations. Breaking down the differences. 1. Execution type. Multi-core processor, designed to run multiple independent tasks at the same time. Each core executes a separate instruction stream to improve multitasking. Example: running a web browser, video editor, and gaming application simultaneously. Vector processor uses single instruction, multiple data (SIMD), where one instruction operates on multiple data points at once. Optimized for handling large datasets efficiently. Example: a vector processor simultaneously performs thousands of calculations in weather simulations. 2. Best for multi-core processors. Ideal for general-purpose computing. Handles multi-threaded applications, AI, and real-time cloud services. Vector processors. Best suited for scientific computing, AI, and physics simulations. Used in applications that process large volumes of numerical data. 3. Power efficiency. Multi-core processors, optimized to balance power consumption and performance. Reduces overall energy usage by distributing tasks across multiple cores. Vector processors, more power efficient for specific workloads where massive data sets need parallel processing. Consumes less power than multi-core processors when performing repetitive mathematical computations. 4. Use cases. Multi-core processors. Widely used in general computing, AI, gaming, and cloud computing. Example: Intel and AMD processors used in laptops, desktops, and servers. Vector processors. Specialized for image processing, AI acceleration, and high-performance physics simulations. Example: NVIDIA's Tensor Cores optimize AI computations using vector processing. Key takeaway: multi-core processors offer versatility and multitasking capabilities, making them ideal for general computing. Vector processors specialize in handling large-scale parallel computations, making them essential for scientific and AI-based applications. Conclusion: understanding multi-core and vector processing architectures is essential for optimizing computing performance in modern applications. Choosing the right processor type depends on whether the workload requires general multitasking or highly parallel numerical computations.